And then I will present a way to actually compute this self-binding energy, which is the original work we have done, and show a way to test our method and conclude with some summary and outlook. So this is a talk about the swampland program. So roughly, just quickly, what is the swampland program about? Is about finding all the criteria to distinguish when an effective field theory can be safely embedded in quantum gravity theory. And there are many swampland criteria that help us to define these boundaries that are organized in the so-called swampland conjectures. And I will focus on the weak gravity conjecture today. What is the weak gravity conjecture? Let me give me a second. Yeah. Let me define it also to fix some notation convention. In the former version of the weak gravity conjecture formulated by Kahneman, Nichols, and Buffett in 2006, the statement is in flat space-time, there in any consistent U1 gauge theory coupled to gravity, there must exist at least a state satisfying this inequality. And today, I want to point out that I will consider it as a statement regarding particles of charge of order 1. So I'm not concerned with black holes. Then the second thing that I want to point out is what happens when you generalize it in case of multiple U1s. And the inequality gets generalized like this. And here I'm taking canonical normalized U1, and I will always be taking canonical normalized U1 in my talk. Otherwise, there is a gauge kinetic function in front of this. But we can, this just for us will be just a sum. In the presence of additional massless Yukawa coupled scalar, a neutral scalar that couples to the charged objects, the inequality gets an additional contribution given by the Yukawa charge, so-called Yukawa charge. This is basically encodes the Yukawa coupling of the neutral scalar to the charge matter. So now I can present some motivation leading to the weak gravity conjecture, starting from flat space-time, and modding out some subtleties that that are always present in this kind of consideration. And I will start from the best known swampland conjecture, which is the absence of exact global symmetries in quantum gravity. You can think about it as a global U1, for example. There are rigorous ways to understand this conjecture, which are based on perturbative string theory and AdS CFT. Namely, you can show, it has been shown by Bex and Dixon that any global symmetry, continuous global symmetry on the worldsheet becomes gauge in the space-time, as well as all the global symmetries in the boundary CFTs corresponds to or associated to gauge symmetry in the bike. And also you can show that if you really try to, under some assumption, if you really try to force the bike to have global symmetries, discrete or continuous, you get some inconsistency on the CFT side by this notion by Hiroshi and Daniel. But there are also less rigorous ways to understand this absence of global symmetries in quantum gravity, which are based on black hole heuristics. For example, you can think about the tension between the no-hair theorem and the finiteness of black hole entropy. So what does the no theorem says? So you can think, it says that a black hole of fixed mass, and you can think about having other gauge charge angular momentum, but in the simplest case, you can just think about the Schwarzschild black holes, for example. This can have any global charge because, and this global charge is not reflected in the horizon, which means that for an external observer, there is an infinite uncertainty, which is associated to an infinite number of microstates associated with the black hole. And so this observer cannot really distinguish if a black hole that he sees, he can just see he can just recognize the geometry, he cannot tell the global charge. So there's an infinite entropy associated to a black hole, which is in contradiction to the finiteness of the Bekenstein-Hawking entropy. Also, you can reformulate this in terms of an infinite number of remnants, black hole remnants. And but in this talk, what I want to focus on is the rephrasing in terms of particles and bound states. So this is a more bottom-up kind of rephrasing, and I will show you right now how you can get an issue, how you will get with the global symmetries an infinite number of stable bound state, which can be an issue. So the Gedanken experiment goes as follows. You can take two copies of the same particle with mass m and charge q. I remember q is the global charge, and take the particle with smallest mass to charge ratio available in the system. So there is only gravity in the system, so this particle will attract and they will form bound states. And you can show that these bound states are stable. Why are they stable? Basically because the bound state mass is smaller than twice the mass of the original particles. And this means that the mass to charge ratio for the bound state is smaller than anything else. It's in particular smaller of the original particle, which is by assumption, we are taking the smallest one, so it's smaller than any other one. And this means that this object cannot decay. Because let me remind you that the decay is possible only if one of the byproduct, or at least one of the byproduct, has a smaller mass to charge ratio with respect to the decaying object. So these objects will be stable, and you can keep going with this process, and you will find an infinite number of bound states. So how can you ameliorate this situation? You can gauge the U1, and in this way you can get rid of this infinite number of bound states. And why is that so? Because now, when you do the gauging, you're introducing an additional long range force. And now it's not clear anymore whether these two particles will form or not a bound state. It depends on the coupling, the charge, and the mass in question. However, if you take the small coupling, if you go in this limit, the small coupling limit, you can see that this dies off, and it's like you're going to restore global symmetry with all the associated issues. So what the weak gravity conjecture tells you is that you better gauge this U1 strongly enough. And what does strong enough means? Since we only have a gauge and gravity, strongly enough means that the gauge force must be stronger than gravity. So the statement that there must exist at least a particle for which gravity is weaker than the gauge force. And this statement was originally formulated as following from a super extremality, which is the condition that allows extreme black holes to decay, but equivalently, as we just saw, can be formulated in terms of self-repulsiveness of at least one particle. And these two inequalities precisely agree. In case you have only gauge and gravity, it's the situation is a bit more complicated when you have scalar fields. So what happens when you have additional massless neutral scalar fields that Yukawa coupled to your charged particle here? So you're adding an additional long range force. So now, if you follow the logic of demanding the existence of a particle which is self-repulsive, you have to take into consideration all the forces. So the scalar forces are attractive, like gravity. So the weak gravity conjecture bound, the self-repulsive bound in 4D here, will be something like this. So the repulsive force given by the gauge U1 must be bigger or equal than the sum of the gauge and of the scalar, sorry, and the gravitational attractions. Here, mu is the, as I said before, yes, is the Yukawa charge, which is encoded in this Yukawa coupling 2m times mu. And this has quite some support from string theory, at least in this, as shown in this F theory construction by this group. And as you can see, they find that there are, so this X is actually the charge. I should have put the charge here. And here I'm showing the red dots. They are showing that the red dots are basically all the states for which the gauge force, okay, is stronger than the sum of the gravity plus scalar. So they are self-repulsive. All these dots, the red and blue are non-BPS states. And you can see that the red dots obey this self-repulsiveness. And yeah, so this is good. This is what we want. And following this logic, we can ask what happens in AdS. So we can follow this logic and demand a self-repulsive particle in AdS as well. And now AdS is quite different from flat space. So in flat space, the forces relevant to this statement of self-repulsiveness are only the long-range one, because you can always take two particles and separate like as far as you want. But in AdS, AdS is confined, right? It's like a box. So we cannot separate two particles arbitrarily far away anymore. And this means that we cannot really neglect the short-range forces, right? So a more accurate formulation that takes this fact into account is the proposed positive binding conjecture. And the statement goes as follows: for a weakly coupled gravitational theory with a gauge U1, there should exist at least a charged particle with charge of order 1 that has a non-negative self-binding energy. So gamma will be the self-binding energy of the particle and cannot be negative. So this was proposed last year by Era and Hofer in this paper. So what is this self-binding energy? And this is computed, it is defined, sorry, as the difference between the energy of the two particle states of lowest energy and twice the energy of the single particle state, again, of lowest energy. In the Hamiltonian formalism, this can be immediately computed using these matrix elements. If gamma is positive, it means that the particle is self-repulsive. If it's negative, it's self-attractive and forms a bound state. If it's zero, either you're dealing with a free theory, but this is like a trivial and we're not interested in, or with a BPS states in interacting theory. BPS are floating objects, so they basically this is the no force condition.
Are you assuming something weak coupling or anything like this when you're talking only about these diagrams? Or you're talking about what is the assumption here? In some sense,
yeah. So I will be. Right now, I haven't introduced them yet, but I will be. So what we are gonna do is we are gonna do perturbative computation. So
but your gamma is non-perturbative. I just want to know what is non-perturbative. Is your gamma non-perturbative well defined?
If its gamma is non-perturbatively well defined, in principle, I think so. But in order to compute it, we cannot really. So what we are gonna do is doing like a perturbation theory, basically, to compute this gamma.
Oh, it's in the first line that the difference of the expectation value of the energy, isn't that a non-perturbative definition? If phi is well defined, that is.
Yeah, this is. So yeah, this is I think it's a good point. I mean, in principle, I would expect this to be well defined also non-perturbatively, but it's hard to see. Yeah, I understand the point. It's hard to see how we can compute it only perturbatively. So
okay, so phi number is not well posed, right? Phi is not conserved.
Phi is not conserved. Sorry, what do you mean?
Does phi has a global charge or not for you?
No, this is already gauged. So
phi is gauged.
Yeah, it's
okay.
phi
so
is
you can talk about
under
charge sector 2. In other words, is that what you mean by this? Charge
sorry, I couldn't.
Are you saying the Hamiltonian in the charge sector 2 minus twice the Hamiltonian in the charge sector 1? Is that what you mean? I just want to give a global definition for this.
May I interpret the claim as saying that in a given conformer, from the point of view of boundary CFT, in a given conformal field theory, there is at least one single trace operator for which this inequality is satisfied. Isn't that what you're proposing? If so, that would be a non-perturbative definition.
So you can go to the CFT, and this quantity actually corresponds to something called like anomalous dimension, which corresponds to the difference between the dimension delta of the operator associated to these two particle states, and the delta, twice delta associated to the single particle state.
Thank you.
Yeah. And so, but we are interested in the AdS, purely AdS story. So we want to compute this gamma at 3 level, and this is determined by quartic interaction of this type. And they can be of 2 types, either contact terms or field exchanges. In particular, we will be concerned with exchanging photons, graviton, and an additional neutral scalar. So we have to do you have to take a set of for such an effective field theory, and this is going to be the set that we take. So gravity is here, the gamma is the cosmological constant is negative, so we are in AdS. You have your photons, you have your phi. Phi is the charged particle under all these photons. The small m is its mass. There is a potential that for notational convention, for convention basically, it's taken to be only the contact terms. So you see all the phi to the 4th and all this type of phi of quartic interactions, which depends on A, B, and C, these effective theory parameters. And then you have your neutral scalar, chi, which has big M as mass, and it's Yukawa coupled in this way. And also, actually, you have to add, since you are hunting for all these kind of vertices, trilinear vertices, you also have to consider this kind of interactions, and which is a irrelevant operator. And you can think about this as coming from the expansion of gauge coupling between this chi and phi. This is the first term. If you take an exponential in front of the kinetic term, basically. But we will see that this will be relevant, important in our computation. So in general, in order to compute gamma, it's quite complicated, but the situation simplifies under assumption of small interactions. This is because you can treat small interaction as perturbation around the free theory for phi. So you can do perturbation theory. This is the standard perturbation theory that you do at university. And this is nice because now the operator and states are those of the free theory, which are really well known. And it's really well known how to quantize a massive complex scalar in AdS. And this is the 2 particle state we are concerned with. So this is the lowest, the one with the lowest energy. So the creation operator, I have a bunch of 0. The quantum number will be set to 0. And if you go to the Hamiltonian, so the Hamiltonian of the entire system is the sum of the free piece plus the interactions. You can just focus on the quartic interaction, because when you plug back this into the definition of gamma, well, what you see is that only the quartic interaction, you can see here, you have to do the contraction, so only the quartic interactions are relevant to this computation. What are these? These are the contact terms, which can be computed using the first order formalism in the perturbation theory, and the exchanges. but the exchanges need, you have to go to second order in perturbation theory to compute these exchanges. So you have to sum over all these alphas, which are the intermediate states. And this is quite complicated. And in general, you're not even sure that you can recast this sum in a really nice way. But we are in luck because there is a shortcut found by one of the same author of the previous paper, which consists in integrating out classically all the exchange fields. So what you obtain in this way is an effective action that is fully in terms of phi. So you will have a free piece plus all the interaction encoded in this effective potential, which is going to be the sum of the contact terms B plus all these additional contact terms that are basically generated by this integration procedure. When you go to the Hamiltonian, now you get this effective Hamiltonian, which is just effective potential, which is done by, which consists by these contact terms and these additional contact terms. And this is really nice because now we can just use first order perturbation theory to compute gamma, because now everything here is a contact term basically. And to give you an idea more explicitly how this works, classically integrating out means taking the equation of motion and plug them back into the action. And this, you can do this really in full generality in any dimension and implicitly. This is the implicit way you do it, and this is the implicit form of the effective contribution of the graviton, the photon, and the scalar. And you can see here that these terms are going to be quartic in phi and y, because here the graviton, the photon, and the scalar obey the equation motion that have as sources. So the right-hand side of all this equation are the sources for these objects that we want to solve for. And the sources are quadratic in phi. And as a consequence, the graviton, the photon, and the chi will be quadratic as well. So this is quadratic, this is quadratic, this is quadratic, this is quadratic, and also this is quadratic, and the source is quadratic. So everything is quartic. But in order to explicit this, then you really have to specify the dimension and solve these equations. And this is what we did in d equal 5 and in d equal 4. So here I'm going to show you quickly the results in d equal 5, because in d equal 4, they are not really enlightening. They are not particularly enlightening in d equal 5 either, but at least they fit in a slide. So, and so this is the contact term, the contribution of the binding energy given by the contact term, which depends on the A, B, and C. And for the photon exchange, this is a function of delta and the sum, as we kind of expected, over the different photon contribution. For the graviton is this one, where delta here everywhere is a proxy. It's a well-defined the CFT, but you can think as a proxy for encoding information about the mass of your phi. Okay. And yeah, if you really want to know, delta is the dimension of the operator associated to this phi in the CFT side. And for unitarity reason, it has to be bigger than 1 in d equal 5. So for the scalar exchange, this is generically really hard to obtain analytically. So we managed to get some analytic expression, these two, in the case of massless scalar exchange, and in the case of BF saturation, when the BF bound is saturated. And in this case, when alpha, which is the additional trilinear interaction between chi and phi, is switched off. Yeah, this is pretty complicated, and this is much nicer. We did also some numerics, also again in the case alpha equals 0, just to check that our analytic expression, namely the BF expression and the massless expression, actually are nicely interpolated by the numerics. And the only caveat here of our approach is that, as any perturbative analysis does some limitations, And the limitation is that this analysis can cover this parameter range here, namely masses of the scalar exchange smaller equal than twice the mass of phi. But this is not really a problem that we cannot cover, like exchange of heavier stuff, because you can always integrate them out and encode the information in the higher order effective operators in V. So this is not a big deal. So given this expression, now we can test our expressions for the self-blinding. We can do two types of tests. One is taking a flat space-time limit, and we want to see if we recover the weak gravity conjecture, the self-repulsiveness version of the weak gravity conjecture in this limit, which we know. And the other thing that we want to check is that it's saturated by BPS states, as it happens in flat space-time. So the test number one, so it's taking a flat limit. Here I'm again doing it in d equal 5. We did it also in d equal 4. The result is the same. And how do you take this limit? This is a little bit subtle. Sorry, you have to take all the parameters in your Lagrangian fixed, and this means that you have to take delta to infinity as well as L. So the positive binding conjecture tells you that the self-binding energy has to be positive. This is the contribution given by the photon, graviton, scalar, and the contact terms on the original potential. And if you take the leading terms in each of these, you precisely reproduce the weak gravity conjecture that we know in flat space-time with two caveats. So there are two observations here. One is the expected behavior of the contact terms that must decay in the flat limit, which is, so it is suppressed with 1 over L with respect to everything else. And the second observation, probably is more interesting, is that this is the contribution given by the additional trilinear coupling that I showed you at the beginning, and given by that more than irrelevant operators. And so this technically, yes, it is suppressed because it's irrelevant operator, so it's suppressed with mass over mass of phi of the charge object with respect to the Planck mass in 5D. But nonetheless, yes, it's suppressed, but it is there. So it's quite interesting that we find this. And then the second type of test is hunting for BPS states, and we want to show that gamma is equal to 0. And we do this in n equal 2, d equal 5, and d equal 4. So this is the theory that we take in d equal 5, taken by this paper, in this paper. So we have one vector, and one gravity, multiply it. And this is the moduli space. And what we do is gauge the U1 square inside this isometry group of the hyper multiplet moduli space. This is the quaternionic manifold. You do so using standard gauge supergravity techniques, and so you introduce this killing vectors that depend on gauging parameters beta and gamma, other than on the hyperscalars. And this is like the gauge, the covariant derivative that you use. You hunt for, after field redefinition, you hunt for AdS supersymmetric vacua, and using, like, satisfying the supersymmetric conditions. And you find the vacuum, and you expand your theory around that. And you find an effective action where all the parameters, masses and couplings, are completely determined in terms of your gauging parameters. So, for example, see here, it's everything is determined in terms of gamma, beta, and also the masses, beta and gamma, etc., etc. I don't want to enter details. I just want to point out that you have two charged objects, phi1 and phi2, and chi is the neutral one, is the neutral guy. And if you focus on phi1, for example, which is the lightest field, you can compute the delta because you know the mass in terms of beta and gamma, and so you can compute the delta, and you can Is there anyone who wants to ask something? I heard. Okay. And you can compute you can plug back in all these parameters, effective parameters, in the expression that we found, and you obtain this. So you may not see it. Yes, it's not obvious, but if you sum up these things, is 0. And if you don't, I mean, you can trust me, I don't know. But if you want to have something a little bit more clear, I can show you what we found in D=4, which is even simpler because now we have only an hypermultiplet, and we can gauge using the graviphoton. So the killing, in this case, the killing vector is only 1 and depends only on beta, which is our gauging parameter. And we do the same thing. We look for SUSY vacua, AdS SUSY vacua. We pick one, and which is this, and we expand around it. So now the effective action is this one. The charge object is again 5, and the neutral scalar is chi. You can work out all the effective parameters, and you can compute, again, you can plug these parameters in our expression for the binding energies in D=4, and you find this. These are the binding energies, and you can immediately eyeball it. So this is the contact term given by, this is the term given by the contact terms, the contribution given by the contact term, which is equal to the contribution given by the scalar exchange. So -3a times 2 is -3/4, plus 5/4 is +1/2, which precisely cancels the gravitational contribution. So the total binding energy vanishes also in those cases. So this is what we have done, and I can, to wrap up, this is the summary and some possible future direction, which are quite a few. And so we motivate the positive binding energy proposal as the right formulation of the weak gravity conjecture in AdS, as the most natural one at least. We described a way to compute this self-binding in D=5 and in D=4, which in general is not that an easy task. And we checked that it survives 2 tests. One is the flat space-time limit, finding actually a new contribution to even the flat version of the self-repulsiveness conjecture. And we checked that for BPS states in n=2, we have gamma =0, as is natural to expect. So what can we do next? So it would be really nice to test this using non-BPS states in string theory. So what we expect to get is to get some self-repulsive, right? So gamma positive. So it would be nice to extend this to fermions and or more charged particles, and check this version with the tower or the sublattice version of the conjecture. You can also add either derivative correction and see what happens, and study the AdS3 side of the story is a little bit more complicated because gauge and gravity are not really dynamical. But it would be interesting nonetheless, because we know that the standard model can be compactified to AdS3. So maybe imposing some kind of constraint like this, you can find interesting constraint on the standard model quantities. And the positive binding conjecture could be also related to super extremality or super radiance instabilities for AdS black holes, and this is something that I'm looking into right now. I'm quite interested in this. And there's also the CFT side of the story that Eran, I believe, is still working on, and checking whether these convexity properties are maybe universal or not in the CFT side, and go back to infer something more generic also on the AdS on the bulk side. So yeah, so this is what I want to say, and thank you for patiently listening to me.